Okay, next problem, number 38. We're given a solenoid with 475 turns. We're told the length of the solenoid is 6 centimeters, it's 0.06 meters in SI. We're told the cross-sectional area is 2.8 times 10 to the negative 9 meters squared. And then we are asked to find inductance. So we have a handy formula for inductance. It's mu naught times the number of turns squared times the cross-sectional area over the length. This would be for a solenoid. So we can essentially just plug everything in that we have, right? This is 4 pi times 10 to the negative 7 Tesla meters per amp, 7, times 475 turns squared times 2.8 times 10 to the negative 9 meters squared. That's cross-sectional area all over 0.06 meters. So we plug this in and we get a value of 1.323 times 10 to the negative 8 newtons over amps. Henry. The unit of an inductance is a Henry. Okay, and for part B, we are asked to find the EMF. We're told that we have a range of a current that goes from positive 2 amps to negative 2 amps. So we have a delta I, which is equal to I final minus I initial, is equal to negative 2 amps minus 2 amps is equal to negative 4 amps. And that's useful because we have an EMF formula, which is negative the inductance times delta I over delta T. And we're told that this all occurs in 8.33 times 10 to the negative 3 seconds. So let's write that down. So delta T was 8.33 times 10 to the negative 3 seconds. So super fast. And we also have a value for inductance. Right? So let's take this. So negative value of this times negative 4 amps over our time. And that was Henry for inductance. And then that gives us a value of 6.353 times 10 to the negative 6 volts. Or we'd say 6.35 microvolts. Okay, next problem. We have number 41. We're given a radius first. This is a solenoid, by the way, with 400 turns. And the length is 20 centimeters. We are told that R, the radius of the solenoid, is 2.5 centimeters. Right? And we need to find the cross-sectional area, which is pi r squared. It's equal to pi 0.025 meters squared. And recall that our inductance is the mu naught times number of turns squared times cross-sectional area over the length of the solenoid. Okay, so if we plug all these values in, right, we just plug these into the formula, then we should get a value of 1.97 millihenries. Then we're asked to find the rate at which the current must change through it to produce an EMF of 75 millivolts. Well, we have a formula It's L delta I over delta T. So the rate would be, the rate of the current moving through something would be change in the current over the change in time. So that gives us E over L, E over inductance, this is EMF over inductance, is delta I over delta T. This is the rate that we want. So what does that give us? We need to enter the EMF, we're told, is 75 millivolts. And we know from finding that the inductance is 1.97 times 10 to the negative 3 henries. So this gives us a rate of 38.07 amps per second. Next problem is a generator problem. Problem number 31. Before we were doing self-inductance. This is generator. And so we're given a situation. Let's see if that works. Okay, good. Where we have a B field pointing into the page, and we have this square coil is able to turn within the B field, right? We're told that the side length L is equal to 0.028 meters. The magnetic field is 1.25 Tesla. Number of turns is 28. Resistance of the coil is 0.78 ohms. And what we're told is that it's going to go from 90 degrees. It's going to go from 90 degrees to 0 degrees in a matter of 0.335 seconds. We want to find the average EMF. So let's recall that the average EMF is, for a coil, is the negative times the number of turns times the change in the flux over the change in the time. So let's put this N over delta T for now, and then consider what is flux. We're going to have a flux final minus a flux from the B field moving through the coil, right? So a flux final minus a flux initial. And this was B times A times cosine of the angle, which in this case was, is 90 degrees. So we have this backwards. Final, we're rotating 90 degrees. Minus the flux of cosine 0 degrees. So this gives us negative times the number of turns over delta T. We can factor out B, A, and then we have 0 minus 1. Well, that gives us N over delta T, B times A. And we have all of the information there where we can just plug this stuff in. All right, so remember this is a square loop and the side is 0.028 meters. So what's the number of turns? The number of turns is 28, so now we have 28 times the B field was 1.25, and then we had 0.028 meters all squared. That's going to be over the time change was 0.335 seconds. Is that right? Yeah, okay, so we plug that in, and then we end up with a value of about 8.19 millivolts. Okay, for part B, we are asked to find the average current. Well, we have our average EMF, right? We know the resistance of the wire, and so we can just use this. So we want average current is going to be I equals EMF over the resistance, millivolts over, what was the resistance? It was 0.78 ohms. Now this gives us a value of 105 milliamps.